Watch the screen closely. There is nothing here, just an empty black visual. You can hear my voice only. Now, you can see a white color background appeared with the text saying hello. Here you got my voice, a visual and a text. These three details, what you perceived, reached to you at a fraction of a second, or say the speed of light. But how is this possible? The answer is electromagnetic waves. Imagine tossing a stone into a pond and you can see the ripples spreading out. An electromagnetic wave is similar, but instead of water ripples, it's ripples of electric and magnetic fields. Now let's take a wave here. The wave has a height, a length and the number of occurrence. We can call this as amplitude, wavelength and frequency. When you increase the frequency, say tightening it, they gain enough energy to pass through objects and even our skin. Yes, that's how X-rays work. But X-rays can't travel long distances through air because they get absorbed. To create waves that can travel much farther, we need to do the opposite. Decrease the frequency and increase the wavelength. That's where the radio waves come in. But what use do we get from these radio waves? It's communication. The communication evolved with a clear path. First, we exchanged voice and audio, then came text and messages, and now with modern networks, we share videos instantly. We initially achieved this through modulating the amplitude, which we call amplitude modulation or AM. Then the frequencies are modulated, which we call it as FM. As computers and mobile devices evolved, communication became far more efficient. The devices work using binary data, streams of zeros and ones. We can assign either 1 for this higher frequency wave or 0 for this low frequency wave, or 1 for this high amplitude wave or 0 for low amplitude wave. Also, a new property was introduced during the evolution of these devices, and it is called phase. One phase equals one cycle of a wave. You can consider this one phase as well. The phase can be assigned either 0 or 1. We can also include more phases like these, with maximum of 8. Today's network uses more phases than you could imagine. But how is this possible? What if you adjust the amplitude and assign a binary value? You get more phases. Now let's put this all together and see how does a cell service work. Whenever you transmit information, the antenna from your device communicates with the cell tower or cell site by means of radio waves. And from there, the signals are converted into digital data. The data is processed and sent to a telecom network hub like Verizon and AT&T. The hub authenticates and routes the data to the receiver cell site, and finally it reaches to the receiver. This happens in reverse too. The difficulties we faced during the evolution is not adjusting the science behind it, but the scalability. The supply must be increased, and it is primarily done by building more cell sites. The cell sites are built into patterns of hexagon. You can notice it anywhere inside a building, in the trees, church, and so on. The cell site has a range, and each range must overlap to get the smooth flow. For each user, a channel is provided. In a cellular network, a channel acts as a pathway for electromagnetic waves. Now let's look at FDMA, the method used in 1G networks. In this method, 832 frequency is allocated for a channel. From the 832 available frequencies, 42 are served for internal network communication, leaving 790 for actual calls and data, and these are split evenly. 395 for inbound signals from your phone to the tower, and 395 for outbound signals from the tower back to your phone. Each cell site belongs to a cluster of 7 cell sites. So the 395 inbound and outbound frequencies are divided among these 7 cells, giving each site 56 channels. With 6 neighboring cells surrounding each site, no 2 adjacent cells share the same frequencies in order to prevent the interference. However, 56 channels per cell site is still limited. To increase the supply, each frequency channel is split into 8 time slots, allowing multiple calls to share the same channel. Now each site can handle 448 call channels. But to further increase the scalability, especially with the rise of computers and mobiles, we got the solution from itself, and it is called CDMA. Let's say Ben, Jane and Carl are in the same room calling their friends. Here we assign a binary value for Ben, Jane and Carl. For these 3 users, a spreading code is given. Let it be 0011, 0101, 0000. Relate the assigned number with the code. If both digits are same, the output is 0. If not, it's 1. So the sequence will form like this. The next step is translating the zeros to positive ones and ones to negative ones. The 3 values are added. You get a composite sequence as -1, -3, 1, -1, -1, 1, 1, 3. A single channel is formed here. What should happen next is the receiver must decode this. To decode the process, the spread code now is translated by zeros becoming positive ones and ones becoming negative ones. Then the 3 spread code is multiplied with the composite sequence like this. The first 4 digit is added and divided by 4, we get -1. Translated and the value becomes 1. Similarly, do the same for next 4 digits and we get -1. Translated and the value becomes 1. Repeat the process for Jane and Carl's spread code. The answer received should match Ben, Jane and Carl's first assigned value, and hence it is decoded. This is how we can triple the use of one channel with assigning a spread code and using some math. But this happens in a large scale. With the explosion of smartphones and the need for streaming data, engineers developed a new method called OFDMA. Think of it like this. Instead of everyone talking in a different codes like CDMA, the network splits the available frequency into thousands of tiny lanes. Each user gets a few of these lanes. Because they are placed very precisely, they don't overlap or interfere. It's like a superhighway with many narrow lanes where each car stays in its lane without colliding. This method is far more efficient for carrying massive amounts of data, which is why OFDMA became the backbone of 4G and 5G networks. When you get the upgrade from 2G to 3G to 5G network, what happens behind the scenes is that smarter people find solutions for these kind of problems. And from these solutions, we end up texting to answering phone calls to watching this video in a much easier way. If you enjoyed this video, hit a like and subscribe. It's completely free, and if you could share any extra knowledge from this, please leave it on the comment section.